All right, here we have another one of our major problems that we run into. It's a little complicated because it requires a lot of moving pieces, but even if it's not particularly difficult math-wise, okay, it's a contact force problem. So in this case, we've got three boxes sliding along the floor. They're being pushed by 100 newtons. Okay, they also have a coefficient of kinetic friction of 0.1. Now, this is very similar if you watch the tension problem. This is very similar to how we treat that, okay? A string attached between two objects is the same as having them just pushing against each other. All right, so we can treat it with the overall. Okay, and we have box A, oh, that's right, A, B, and C. Okay? So we separate into those pieces. Now overall is going to be the simplest one to do. We know the net force is going to be, well, let's talk about the forces on it. First off, we have the force of the push. Okay? We know that's 100 newtons. Next, we have the force of friction. Okay, and we can find that with the normal force times coefficient of kinetic friction. And in this case, the normal force is going to be equal to the force of gravity, which is equal to 100 times, oops, not 100, 40 times 9.8, which gives us a frictional force of 1.52. That's not right. Sorry, frictional force of 39.2. Sorry. And then that gives us an overall net force of 60.8, which gives us an acceleration of 1.52. All right? Now, we want to find the contact force between A and B and B and C. So let's start with A. Okay, you tend to want to start with this one because this one's going to have the fewest forces on it. We can see that by analyzing it. Okay, the forces on A are the force between A and B, okay, which we're trying to find, and the force of friction on A. And we can find that pretty simply by taking 10 times 9.8 times 0.1 equals 9.8. Alright? B is going to have the force of A on B, which we still don't know. The force of friction on B, which of course I'm going to just do quickly here, is 16 times 9.8 times 0.1 equals 15.68. It also has the force of B on C, which we don't know. Okay? So that's three forces. A only had two forces on it. C is going to have the force of the push, which is 100, the force of B on C, which we don't know, and the force of friction, which again we can find 14 times 9.8 times 0.1 equals 13.72. Okay? So, starting with this one that's got the fewest forces. Now, what's the one thing we say about any objects that are connected? They must have the same acceleration, otherwise they'd split apart. So that tells us that this one is going to have a net force of 1.52 times 10 or 15.2. Yeah, I'll be 2 minutes. 15.2. All right? So, to that we get that 15.2. If I can write better. 15.2 is equal to force of A on B minus 9.8. And it's minus there because the force of friction is, of course, opposing motion. We get that, we get the force of A on B equals 25. Now, Newton's third law tells us what? That this, of course, has to be the same as this. So now we know B's is 25. Now, at this point, these two problems are equally easy to solve. They both have three forces, of which we know two. But we'll do both of them just to make sure everything's right. Okay? F net equals 16 times 1.52. Okay. Multiply that out, we get 24.32. Okay. We set that up, 24.32 equals FBC minus FAB minus force of friction on B. Okay, it is both minus because the FAB is me pushing backwards. This is going to come out to be FBC is equal to 65. Finally, we got this gap. Okay? Now we already know this FBC, we just found it, but let's confirm that it's correct. Alright, so we have F net equals 14 times 1.52 or 21.28. So 21.28 is equal to F push minus FBC minus force of friction C. So I'm going to add that there. And then we get 21.28. Cannot write today. 100 minus FBC minus 13.72. And we get FBC is equal to 65. Again, showing that Newton's third law does apply. Wow, can you see all of that? Awesome, you can. Sweet. All right, hopefully that makes sense. Okay, we've applied, again, overall and each separately, and that's how we've gotten to work out. Awesome.